Hello everyone, welcome to the 31st lecture in the series. In this lecture, we are going to learn about minimum spanning trees in detail. In specific, we are going to study what minimum spanning tree problem is and how we could address it with the help of two algorithms, namely Prim's and Kruskal's algorithm. Of course, with this lecture, we will be learning or putting our attention to Prim's algorithm only. We will be seeing an example of how to solve it and also the algorithm and its analysis. First, we should know what minimum spanning tree is. Given a graph, we are going to convert it into a tree, and as the name says, it should be a spanning tree, which means we should cover up all the vertices in that graph via this tree, and we should be able to span all those vertices through the edges with the least cost, and that is going to be a minimum spanning tree. So, with this lecture, we will be seeing some of the real world applications of this minimum spanning tree algorithm, and then we will see with an example how this algorithm could be used. So, first consider the problem of laying a telephone wire. As you see here, we have a central office and we have many houses to which this telephone connection has to be extended, and the possible solution via a naive approach would be looking just similar to this. So, from the central office we will be extending separate connection to each of those offices. But when you go with this naive approach, the problem would be that we may have to spend a lot of amount on the cost of the wire, and so we say that when we lay telephone connection via this approach, then it is going to be expensive. On the other hand, a better approach would be like we are trying to group together houses that are at a one hop distance from each other, and thereby from central office we are extending a connection to one of those houses, and from there the houses that are at one hop distance are all getting extended with the same connection. So, when we go with this approach, the advantage we would gain is that when you take into account the total length of wire we spend on extending connection to all those customers, it is going to get minimized. So, this is what exactly we are going to do with the help of this minimum spanning tree. So, given a graph, we are trying to find a way to connect all those vertices through the edges with the least cost. So, similarly, the same thing can be thought of for some other domain, like given a networking domain. So, we are given with some set of data centers, as you could see here with the yellow bubbles, and those are regional data centers, and we want those regional data centers to be connected with high speed data lines. So, out of all the possibilities we have, we are supposed to choose the line that has the least distance. So, for this can think of using this spanning tree algorithm, so that we will be able to find a way to link all those regional data centers with the minimal total cost. So, here for instance, we can assume all those regional data centers to be vertices in a graph, and our objective is to connect all those centers via the cheapest cost. So, here we have picked up those edges with the least cost in such a way that they extend connectivity to all those regional centers, and of course, when we use that approach, this is going to be the total cost of that of reaching all the vertices in that particular graph. So, considering this, now we define what that minimum weight spanning tree problem is. So, given a connected graph, and in that graph we have all non-negative weights on that edges, we are supposed to find the spanning tree T, for which the sum of weights on all the edges is as small as possible. So, that is why this tree has got the name as minimum spanning tree. So, we should be able to graph into a tree, and when you sum up the weights of all the edges in that particular tree, then its cost should be as small as possible. And one of the question that may arise at this point of time is, why not we try all possibilities in order to build a minimum spanning tree. For instance, if we assume that the graph has n vertices, then the total number of spanning trees that can be constructed with such a graph would be n power n minus 2, where n represents the number of vertices on that graph. Say if we take a value of n as 75, then it comes to a huge number like this, and in such a case it is not wise to try out all possibilities of minimum spanning trees for a graph. So, we stick on to some algorithms. So, in this particular lecture we are going to learn one of those algorithms developed by Prim. So, the minimum cost spanning tree problem is defined here. We have an connected and undirected graph, and in that graph all the edges have some weights associated with it, and so we call this graph as a weighted graph. Now, the cost of the spanning tree would be the sum of cost of all its edges, and one among those trees would be called as a minimum cost spanning tree, provided in the tree all the edges when it summed up yields the lowest cost. So, here you are given with an weighted and undirected graph, and the particular graph has 6 vertices, and it is one of its minimum cost spanning trees. So, likewise, given a graph, there is a possibility for us to have more than one spanning tree. A spanning tree is one that extends connection to all the vertices in that graph via any of the edges, right, and we call any one of the spanning trees as minimum cost when we sum up those edges cost, and if the cost is going to be minimal, then we call it as a minimum cost spanning tree. So, these should be true for a minimum cost spanning tree. So, a minimum cost spanning tree is actually a subgraph of an actual graph such that it is actually a tree, which means it is not supposed to possess any cycles, and so we say that it is acyclic, and it should cover up all the vertices in that graph. Whatever vertices the graph G contains, the resultant tree should also contain all those vertices, and the resultant tree should contain exactly v minus 1 edges, and the total cost associated with the tree edges is going to be the minimum among all the possible spanning trees that are constructed for this particular graph G. And always the minimum spanning tree is not necessarily to be unique. We can have different kinds of spanning trees for a given graph G. So, these are some of the applications where this minimum spanning tree algorithm finds its use. One of the prominent applications is what we saw before, like extending connection, telephone connection, or extending linking all the data centers. And for instance, if we imagine a printed circuit board, then routing all the wires, and when it comes to city planning, then how to go for laying the sewer pipes, and in case of road planning, wherever we have to link certain things via some shortest path, the shortest cost or the least cost, then it is wise that we go with using this minimum spanning tree algorithm. And for content distribution with internet, and also for providing heuristics for traveling salesman's problem, this minimum spanning tree algorithms are quite useful. So, as we have learnt so far, for this minimum spanning tree to be built, the input should be an undirected and weighted graph, and we assume that graph to be G with set of vertices V and set of edges E, and all those edges have some weights associated with it, and all those weights are non-negative, and the output would be a minimum spanning tree G, and its total weights would be minimum. And we are going to learn two greedy algorithms for finding the minimum spanning tree given a graph. One of them is Prim's algorithm, which we are going to cover up with this lecture, and Kruskal's algorithm we will be discussing with the next lecture. And these are the assumptions that we are going to make with building this minimum spanning tree. First and foremost, the input graph should be connected. If the graph is not connected, then there is no way of building a spanning tree. And in order to check whether a graph is connected or not, you could use any of the search algorithms that we have learned before, namely the breadth first search or the depth first search algorithm. So, if you are able to find a tree from a graph, then it means that all the vertices in that graph could be reachable, and we say that the graph is connected. For disconnected graphs, we may have to find the minimum spanning forest. It is not possible to have a tree. When the graph is disconnected, we will have multiple trees, and in such a case we call the set of trees as a forest. The second assumption is that all the edge weights are distinct. So, here why we explicitly say that the edge weights should be distinct is that if in case the edge weights are not distinct, then there is a possibility that we can have more than one minimum spanning tree with the same cast, and the algorithms remain correct with arbitrarily breaking ties, and when you look at analysis it is going to be slightly complicated. So, always we say that the graph should be connected and the graph should have weights associated with the edges and all of them should be distinct. So, as I said before, we are going to study about two algorithms, one by Prim and other by Kruskal. With the Prim's approach, we are going to build that spanning tree in an incremental fashion. First, we would be picking up the edges that are at a low cost distance from the start vertex. So, then we try to build the spanning tree in such a way that just by adding an edge to start vertex, the resultant does not end up with a cycle, and we will be continuously doing this and try to expand the tree. In case of Kruskal, first we will be building a forest and finally that forest will yield us a tree. So, we will be picking the lowest cost edge that is not yet in a tree and that does not yield a cycle, and we will be first and foremost sorting up all the edges in that graph according to their weights, and we will be picking up the edges that have the least weight with them one after the other in such a way that upon including that with the tree it does not end up with the cycle. So, by the time we start this Kruskal's algorithm, we will be starting with the forest, a forest in such a way that whatever vertices the graph contains, each of those vertices are independently treated as trees, and we say that we start with the forest and end up with the tree with the Kruskal's approach. So, this is the Prim's algorithm in CRISP. So, here we maintain a set capital R which is a subset of V and a tree capital T spanning vertices in R. And we are going to build a tree. In the tree we are going to include all those vertices. So, this V of T should have all the vertices in capital R, and we are going to grow R by adding one vertex after the other during every iteration, and we are going to add a vertex to this tree by in such a way that the particular vertex is not already present, and it should have the least cost. So, initially R will be having the start vertex alone, which is a start vertex could be any arbitrary vertex, and its T is going to be null or empty, and then we are going to select a minimum crossing edge from R to R bar in such a way that its cost is minimal. So, these two algorithms are actually employing a greedy approach. So, which means we do not stop at a point when a solution is reached, rather we will be trying to find all possible ways of finding the solution, and among that we are trying to find the optimal solution, and that is what we say as a greedy approach. And finally, we will be adding V to R and E to T only if this condition is true, that is if that edge is with the minimal cost. So, we take into account the weight of the edge and that should be minimum. So, if that is the case, then we will be adding V to R and E to T, that is edge E is added to the set T and vertex V is added to the set R. So, as you see here, we proceeded with the start vertex, and from the start vertex I have chosen the edge. So, only two edges are reachable from the start vertex, and as such this is shown highlighted, which means this is the edge that has the least weight with it, and so it has been chosen. Likewise, from here then we take into account what are all the edges that are reachable from the vertices that are marked visited. From this vertex is reachable, and from S this is also reachable, right. So, we will be choosing this particular edge just because this edge has the least cost compared to this, and so that has been shown highlighted. Likewise, we may try to choose the edges with the least cost during every iteration, and we will end up with the tree, and the tree should include all the vertices that are part of this graph. So, Prim's algorithm, it is much similar to Dijitra's algorithm that we learnt before. It is also following the greedy approach, and similar to that, Prim's algorithm is one of the algorithms that follows the greedy approach. So, to start this Prim's algorithm, we have to pick up an arbitrary vertex as the start vertex, which we call it as S, and then we grow the minimum spanning tree as a cloud of vertices starting from the start vertex S. We store with each vertex V a label called d of V, where d of V is the smallest weight of an edge connecting V to a vertex V in the cloud. So, we have the set of vertices that are part of the minimum spanning tree in the cloud, and we try to add more and more of vertices to that cloud. So, at each step we add to the cloud a new vertex u that is outside the cloud, and it has an edge associated with it with the smallest distance. And if we are able to find one such vertex, then we will be updating the labels of the vertices adjacent to u. So, after adding this new vertex onto the cloud, we will be adding those edges that are reachable from the newly added vertex, and then we will try to find the minimal from that. In such a way, we will keep on proceeding. So, this is the actual Prim's algorithm. Initially, we have T represents the spanning tree, and the spanning tree will be containing only the start vertex, which is S in our case, and we are going to have another set E, which is the set of edges that are adjacent to the start vertex. So, these are the initialization parameters for this algorithm. After that, we are going to do the entire thing till T does not contain all the nodes. The stopping criterion is we are reaching a situation that is a tree where the tree includes all the vertices from that graph. So, while the that is the tree does not contain all the nodes, we are going to repeat these steps. So, we are going to remove an edge v comma w, where v and w represent two vertices and that has an edge between them, and the edge between them has the lowest cost. And if suppose that w is already in T, then we cannot again include that vertex. So, in that case, even if we are able to find one such edge with the least cost, we are supposed to discard that edge. Otherwise, we are supposed to add that edge and the node w to the minimum spanning tree, and then add to E the edges that are all adjacent to w. So, you know that what are all the edges adjacent to a newly visited vertex is maintained in E, and so now we have added a new node w to the spanning tree, and so we are just adding up the edges that are all adjacent to w to the set E. So, we will be repeating this till you are able to bring in all the vertices that are part of the graph into T. And in order to find the edge with the least cost, we can use any of the data structures that we have learned before, like we can have a list or we can have a priority queue being implemented. So, if in case we have a list, then we may have to make a search from beginning till end every time to find the edge with the least cost. If suppose we have that priority queue version, then it helps a lot. As you know, in a priority queue, whenever we do the delete min operation, always it returns the minimal element from the data structure, right. So, we can have priority queue implementation to find the edge with the least cost. And here always we need to make a check that whether we end up with the cycle, because as you know, we are building a tree, and in a tree you are not supposed to have any cycles, right. So, testing for cycle is automatically done with the help of this Prim's algorithm. So, when you compare the implementation aspects of Prim and Kruskal, Prim is relatively simpler than Kruskal's algorithm. Now, we will see with an example how this Prim's algorithm actually works. Let us assume that we have this graph that contains 6 vertices, and we have you could see that this graph is an undirected graph, and it has weights along edges, and so it is a weighted graph. And you could see that all the weights are all non-negative, and we randomly choose one vertex as the start vertex, and so initially our vertices set contains only 1, and our edge set E dash is empty. In the next step, what we do is that we add up what are all the vertices that are reachable from vertex 1. So, you choose the vertex u that is not in V such that the edge weight from u to V in u to a vertex in V is minimal. So, here from 1 we have 3 vertices reachable, namely 2, 3 and 4, of which reaching 3 is with the minimal cost of 1. And so, I just add vertex 3 to my vertex set. So, now the vertex set includes elements 1 and 3, and this is the newly connected edge which to our edge set E dash. So, this edge is between 1 and 3, and so it has been added to the edge set. So, always you need to know that in a edge set we always represent an edge as a pair of vertices, and so we have the edge set being added with an element 1, 3. So, we have to repeat this procedure until all the vertices have been added up to the tree. So, next we have to choose the vertex u that is not in V such that there is an edge from V to a vertex in V and the cost is minimal, right. So, now we have certain other possibilities, like now we have visited 1 and 3. So, from 1 we have 2 other paths that is not yet explored with the cost of 10 and 5. From 3 we have 3 other paths that is not yet explored, like 2 at a cost of 8, to 6 at a cost of 6 and to 4 at a cost of 3, of which reaching 4 at a cost of 3 is minimal, and so it has been chosen and added to the cloud. And so, now the cloud contains elements 1, 3, 4, and this is the newly added edge, and so we have added the vertex set, I mean pair of vertices like 3 and 4 to the edge set. And in the next step we begin exploring 5 because it is the one with the least cost. So, we add up 5 to that set, and as such this new edge gets added to this set. So, we will be keeping on doing this till all the vertices in that graph are added to our vertex set V, and associated edges are all in the edge set E dash. And since we are supposed to find the edges with the minimal cost, ultimately towards the end we will be summing up all the cost associated with the edges that you find in E dash. So, as such after reaching this vertex we have chosen 4, and next to that you could see that 5 is marked visited, and so from 5 we have one edge with the least cost which is 1. So, this edge is added, 5, 2 is added up here, and once we reach 2 we are able to reach 6 at a cost of 1. It is also an edge with the least cost, and so it has been added to the edge set. Once all these edges are added to the edge set, you could see that all those corresponding vertices have been marked visited. Now that we have visited all the vertices in that graph, and so we say that we have constructed a minimum spanning tree, and the cost of the tree is going to be the sum of cost of all the edges in the edge set, which is 10 in this case. So, for finding the minimal spanning tree, of course, we are using two properties, namely the cycle property and also the cut property. So, what cycle property says is that if suppose we are given with a graph, and in that particular graph if we have one particular edge with the highest cost, then that particular edge can never be part of the minimal spanning tree. That is what we say as cycle property. If suppose I try to include that particular edge with the highest cost onto the tree, then that will ultimately end up in a situation that we have cycle in that tree. So, that is what this cycle property says. So, let T be a minimum spanning tree of a weighted graph G, and let E be some edge of that graph G that is not in T, which means it is not part of our spanning tree, and let capital C be the cycle formed by this particular edge E with T, and for every edge f of C, this weight of that f will always be less than or equal to weight of E. So, here we can prove the same by contradiction. If suppose the weight of f is greater than weight of E, then we can get a spanning tree of smaller weight by replacing E with some f. So, that is what we have shown here. In this case, we have considered this f to be an edge with the highest cost, and so here for the sake of constructing this spanning tree, we have chosen some other edge E. In our case, it is an edge with cost 7. and this edge has replaced this particular edge, thereby we are able to construct a spanning tree. And next is what cut property is. So, what cut property says is that whenever we do a cut, automatically the graph would be chopped into two pieces, right. So, the edge that has resulted in partitioning the graph into two by the result of a cut operation will always be part of a minimal spanning tree, because without that edge we will not be able to construct a tree, otherwise the graph would get disconnected, right. So, that is what we mean as a cut property. With cut property, what we say is that that particular edge that results in disconnecting a graph would always be part of the minimum spanning tree, because without the particular edge we cannot have the resultant tree as connected. So, consider a partition of vertices of G into two subsets U and V. Let E be an edge of minimal weight across the partition. There is a minimum spanning tree G containing this edge E. There will always be a minimal spanning tree G that will include this particular edge E. So, as an example here you could see that let T be the minimal spanning tree. We have a spanning tree, whatever lines you see here as bold, that is part of the tree. Let us say that if T does not contain the particular edge E, in our case let us assume this to be E, and consider that a cycle C is formed by E with T, and let F be the edge of C across this partition. This is our F here. So, by cycle property we say that weight of F will always be less than or equal to weight of E, and so weight of F can also be equivalent to weight of E. So, we can obtain another minimal spanning tree by replacing F with E. So, this F can be replaced by another edge in this graph, say E. So, what we say is that if suppose this particular edge is not part of that graph or the tree, then the tree will be left disconnected, but our objective is to have all the vertices in that graph. So, it is must that this edge is always part of that spanning tree. So, for Prim's algorithm, as I said before, we will be picking up one vertex as start vertex, and then we will be trying to add more of vertices onto the tree in such a way that every time we pick up an edge that has the least weight among the set of edges we have. So, let us consider this example. So, in this example we have picked up 1 as the start vertex, and from 1 we have 3 paths, and of which this is the least, and so we have taken up this, and now we have reached 3, and now we have 4 other possibilities like this, and 2 other possibilities that we have not yet touched from 1. So, from among these 2 and from among these 4 possibilities we have to choose the one with the least. So, ultimately this 23 would be the least, and so we will be picking it up next. And after marking 5 as visited, number of options has got increased. So, we have 2 more options from here, and so we are supposed to pick the one with the least cost, and that is how we picked up 32. And then again from after reaching 2, we have a few more possibilities, and of which the minimal was 31. And after that reaching 4, we have considered the available possibilities, and of which reaching out 8 at a cost of 29 is least, and so we have chosen this. And at last we have chosen the edge with the least cost as 54, and thereby we are able to extend connectivity between vertices 1 and 6. So, when you sum up the cost, this is going to be the total cost of this minimal spanning tree. And here you could see that we have one more example where we have taken A as the start vertex, and from there we have reached all other vertices in that graph. So, from A we have reached B, and then B to D, and then D to C, and then C to D to F, and C to E. So, likewise we have constructed the minimal spanning tree. So, here as you see here, some of the vertices that were initially constructed to be part of the spanning tree have been later avoided. So, here you could see that initially from A the vertex B was reachable at a cost of 2, and so it was marked visited, and then at this step after reaching B, the options are one to reach C at a cost of 5, and another to reach D at a cost of 7, and another to reach E at a cost of 7, and of which 5 was minimum, and so we chose this. And after reaching here, we have plenty of options like to reach A at a cost of 8, reach E at a cost of 8, and D at a cost of 9, of which we have picked up 7. So, these edges are never going to get used, and so it has been shown dotted. And after reaching 7, we could reach F at a cost of 4, and so it is part of the minimal spanning tree, and we could reach from E F at a cost of 3, and so it is part of the tree. So, but if we add up this to the tree, then we will end up with a cycle, and so we do not add this, we stop at this point just because we have reached all other vertices at some shortest or least cost. And here you could see that from F finally we reach out to E using this cost of 3. So, here you could see after reaching, initially we had reached E at a cost of 7. Now that we have found an alternate way via F to reach E at a cost of 3, as such, since this is a greedy approach, now you see that the link between A and E is shown with dotted lines, which means it is never part of the spanning tree, whereas we have found a way to reach E through F at a cost of 3. So, this is going to be the spanning tree with the minimal cost for us. So, in the beginning I told you that the minimum spanning tree for a graph is never going to be unique. For a given graph, we can have multiple spanning trees, and among the spanning trees there is a possibility that we can have a spanning 2 or more spanning trees with the same cost. So, here as an example I have shown a weighted graph here, and this is one of the spanning tree for this graph, and of course, the cost is 34, and these two minimal spanning trees for the same graph, and of course, you could see that for both the spanning trees the total cost is 31. So, we say that minimal spanning tree does not have to be unique for a given graph. So, we have already seen the algorithm presented to us by Prims. Now, we analyze its complexity. So, initially for each of the, we have set of vertices, and for every vertices in that particular graph, whatever edges that contain and whatever weights that edges contain, we will be putting up in this key, and so for every vertex we have to do this, and so that will take up a time of order of V. And after that, within this loop, what we do is that for every vertex that we have marked visited, we will be trying to look at its edges, and from among the edges we will be picking up the edge with the least cost. For doing so, we can have a heap implemented, and for in a heap your delete min operation will have a complexity of order of log V, and for every such vertex that you have found, you may have to add up all the vertices, I mean edges that are all connected to that particular vertex, and so for all the adding up all the edges, it is going to take up a cost of order of E. And finally, we are going to do delete min operation every time, and we will be updating the weights, and for that we will be taking up a time of order of log V, and when we sum up all of these, then the total complexity of this algorithm would be order of E log V. So, when we look at the algorithm analysis again, if in case we do not use a heap and that we use a list for finding the minimal element from the set of edges available, then that is going to take up a cost of order of V square. If in case I make use of a heap, then it is going to take a cost of E log V, and so that the total cost of Prim's algorithm would be order of E plus V into log V. So, alternatively, this Prim's algorithm can be done with another approach too. With that, what we have to do is, first of all, we have to create a forest of trees from the set of vertices on that graph. Then we try to merge trees by adding safe edges until only one tree finally remains. So, here we need to know what a safe edge is. A safe edge is one that contains the minimum weight, and by adding that edge into the tree, we do not end up with a cycle. If we are able to find one such edge, we call that as a safe edge. So, we start with forest, and we try to bring in all the vertices into a tree by taking into account only the safe edges. So, here initially for this graph, if we have to convert it into a forest, then it should be 5 different trees. Each of those vertices should be treated as separate trees. Then we try to merge the vertices into one tree in such a way that we pick up a safe edge. A safe edge is one that has the minimal weight and that does not end up in a cycle. So, this is also another way of implementing this Prim's algorithm. So, to summarize what we have seen so far, the purpose of Prim's algorithm is to construct a minimal spanning tree from a connected, weighted and undirected graph. Thereby, it should minimize the total edge weights. The approach that Prim's algorithm uses is a greedy approach. So, it grows by starting from any vertex and tries to build a minimal spanning tree. It repeatedly adds the edge with the smallest cost associated with it, and by connecting a visited vertex to an unvisited vertex. So, it repeats this step again and again till we reach a minimal spanning tree. And in order to construct this minimal spanning tree, we will be using the data structures, namely queue or a priority queue or a list. As I said, if we use a priority queue, then the cost would be cheaper than implementing a list, because in a list, if you want to find the minimal element every time, we may have to search from beginning till end, and so it is wise that we use a priority queue implementation here. And when we talk of time complexity, efficient implementation using heaps and adjacency list will give us a running time of order of E log V. And when it comes to edge selection, always Prim's algorithm chooses the edge with the least weight, and the edge upon adding into the tree should not lead us to a cycle, and that is how we pick up edge every time. And when we talk of applications of this minimal spanning tree, as I said before, mainly in networking design problems like laying cables or roads, this particular algorithm is very essential, as it brings down the cost of implementation of the same. So, hope you are thorough with the Prim's algorithm by this time. With the next lecture, we will be learning about Kruskal's algorithm.